Hey everyone, welcome back. In this video, I am going to switch gears a little bit. I say switch gears because most of my regular subscribers know that my primary focus is on image processing, especially scientific and engineering type of image processing. But natural language has become one of the key aspects of no matter what you're trying to do, whether it is science, engineering, law, whatever field you are. Natural language processing can be extremely useful in your specific field. So I thought, why not take a couple of videos in talking about natural language processing. And also, you must be living under a rock if you don't know what is going on in the field of natural processing, especially with GPT. So it makes even more sense for you to understand exactly what in the world it is and how GPT works, and possibly train your own GPT. Not a humongous model like GPT-4, but train your own GPT, GPT-2, for example, and on your own documents. So if you have a whole bunch of research articles that you never have time to read, and you can throw them at your own GPT, train your GPT, and then say, hey, GPT, can you summarize this or something else? And these are the type of applications I'm thinking in my mind when I thought of creating this video. If you want to be notified on future such videos, again, this is the time to hit the subscribe button. And also, if you're feeling extra generous, just look for the thanks button right next to it and feel free to contribute. Okay, with that information, let's go ahead and jump into these few slides. In this specific tutorial, I'm not going to do any coding. Let's save that for the next tutorial. So do not forget to hit the subscribe button so you are notified when that one comes out. So the goal here is to understand what these language models are, and with a special focus on GPT. And as you can see on the screen, there is a quick a snapshot of a transformer network. If you already know what that is, you probably are one of the few people who have done your homework. Okay, first of all, just to make sure everyone is on the same page, what are language models, right? They are the foundation for any natural language processing tasks. So some of the terms that you hear in the context of natural language processing are GPT, BERT, and just large language processing like LLP. There are a lot of acronyms that people use, but basically these are language models that are the foundation for many natural language processing. What do we mean by that? They help machines understand how to generate human language, right? I mean, it's not like, okay, take word to word and then just translate it. That's easy. Then it's just a lookup table. But that's not how natural language actually works, especially even if you stay within a specific language. Even within English, that's not how you form sentences or you give a response to a certain question. So natural language is completely reliant on the context. Okay, what do you mean by that? And we'll get to that in a minute. So over the past few years, there are a lot of algorithms that have been developed. I mean, you probably heard of LSTMs, for example, but lately in the last 1 to 2 years, since 2019, let's say, it's almost like an exponential rise, right? And in fact, this year itself, in 2023, last few months, you heard about ChatGPT 3 and now ChatGPT 4 with the trillions of parameters. And I don't know when ChatGPT 5 will come, and I'm scared in terms of what the capabilities are, but curious at the same time to learn what they are when they come out. So since I just mentioned about LSTM, these are the early breakthrough in language modeling. Why do I say early breakthrough? Because these were introduced in a long time ago, 1997, but they are a type of recurrent neural networks. But RNNs came with certain limitations. I have done a video on that, and in fact, I have a line here that talks about exactly what the key limitations are. First of all, they struggled with vanishing gradient problem, making the training process very difficult. So especially when it comes to capturing the context over long sequences. So you're writing an article. Let's say you want the natural language processing like GPT-4 to write an article for you. It has to know what happened like 2 paragraphs ago, right? Forget in fact, in future, we may have a model that can actually remember what happened, I don't know, 2 books ago, 2,000 pages ago. But at least it needs to know what happened a few sentences ago. But RNNs struggled with that. And LSTMs exactly addressed that issue. because they introduced a unique architecture like gating mechanisms, and it enabled them to remember or retain this information. And if you don't know what I'm talking about, you can go ahead and search for my video on my channel. I have done a video on this topic a long time ago. This was video number 167, and the one that I'm about to record is, I think, video number 308. So that was a couple of years ago that I have done this, where we generated some text. Now see how far we have actually come along in the last 1.5 years or so. Okay, now transformers actually revolutionized this entire thing, natural language processing. Transformers in 2017 was the paper that was published by Vaswani and group. And the key, I should say, the key functionality or the strength that it actually offered was self-attention and being able to parallel process. Because these are sequences, right? So how do you parallel process these sequences? And transformers actually allowed that. And a transformer, it's based on encoder-decoder network. So if you look at this image on the left-hand side, the block that you see is an encoder. On the right hand side is the decoder. Just like images, like I did encoder decoder for images, right? So you take an image and you encode it, and then you reconstruct the image back, or you train a model on a whole bunch of images using an encoder, and then you embed the findings of these images or features of these images into a vector. We call it a noise vector, and in future you can kind of play with this noise vector or latent vector to generate new images in future. Very similarly, here you have an encoder and a decoder. You train the encoder with a whole bunch of text, and then you kind of capture the information as an encoded representation, and then you use the decoder by playing with this latent space in terms of generating what you want to do. So as you can imagine, decoder is the generation part, encoder is the training part. In fact, encoder, its job is to process the input sequence. Our text is nothing but input sequence, and its job, encoder's job, is to take the sequence and generate a contextualized representation of each token. A token can be a word, or it used to be a word, but now you can have a partial word as a token. So if you have a sentence, each word can be tokenized, meaning represented by a specific number, let's say, and then that is what's going into, that's how the sentence is represented. And And how many tokens you have completely depends on the vocabulary that you have in the training text. If your training text has 5 words, so possibly the size of these tokens, the number of tokens that you have is 5. It could be less than 5 because some words repeat, and it depends on how you encode it and all that stuff. Again, please read the original papers so you get some idea in terms of what these terms actually mean. But in this video, I will try to explain a couple of terms that are relevant. And decoder is its job is to generate an output sequence step by step using the encoder's output as an input. So it takes an input, and a decoder's job is to provide you a sequence, and it goes from left to right. Because it doesn't know what's going on. In fact, I have a slide on that. Let me not talk a lot about it. Here it is. So first of all, I mentioned about transformers providing 2 different things, right? So self-attention and being able to parallelize the training process. So self-attention, what is it? It allows the model to weigh the importance of different words in a sequence. Okay, what does that mean? I'm just reading off the screen. What it means is, for example, I actually have an example in a second, but it's a mechanism in these transformer models where it allows each word in a sequence to attend to all other words in the sequence, meaning each word in a sequence has a meaning, right? In a sentence, every word has a meaning. There is a reason why you're using that word in that specific sentence. For example, in this case, in the sentence, the cat climbed up the tree and it was so tall. When I read that sentence out, especially for those of you who grew up at least listening to or speaking English, you should immediately realize that it's the tree that it was tall, not the cat, right? So the cat climbed up the tree and it was so tall. In this case, it is referring to the tree, not the cat, right? I'm pretty sure most of you know that. And if you don't know that, then you're probably, you have limited English vocabulary, and I totally appreciate that, right? So you're probably with English as I am with Spanish. I think I understand, but I don't. Okay. Now moving forward. So what does this self-attention do? It actually assigns more weight to the words or to the tokens tree and tall. So when it's processing the word it's looking at the word tree and tall because it's adding more weight to that compared to cat or climbed, compared to the other words. That's exactly what self-attention is. And this is what transformers actually brought into the picture, and this is what revolutionized this natural language processing. And of course, being able to parallel process means we can throw a whole bunch of data at multiple processors, multiple GPUs, and train them in a decent period of time. If you don't do that, then it takes, 2,000 years to train something, but as opposed to, 20 minutes. So, well, not 20 minutes, but probably 20 days, let's say. Okay, now moving on, there are two primary types of NLP. You'll hear two different terms. You probably already heard of them. One is BERT and the other one is GPT. GPT is more famous because most of us use it or interacted with it or heard about it. But BERT stands for bidirectional encoder representation from transformers. That's a mouthful. What that means is when you have a sequence of text, you're reading, like for example, when we have this text, the cat climbed up the tree, right? So the cat climbed up the tree and it was so tall. When GPT creates this, it's creating it from left to right. But what BERT, when it is actually training, like the BERT models, they're actually focused on the encoder side, and what it's looking at is BERT stands for bidirectional. That means it's looking at the statement from left to right and right to left, because the context has to make sense. So that's exactly what BERT is doing, the bidirectional part, and it's well suited for tasks that require the understanding of the context. Because to generate a text, you don't need to know what's at the end of the paragraph. You're just generating, and you'll take care of it when you get there. But when it comes to certain applications, for example, sentiment analysis or semantic role labeling or text classification, you're trying to understand left to right and right to left. That's exactly what BERT is good at. And GPT, I'm pretty sure most of you know what it stands for. It's generative pre-trained transformer. Generative because it's generating text. We know that. Pre-trained because it's actually, you're not doing any training. You're asking it a question, for example, if it's a chatbot type of application, and it's giving you an answer. You're not training it with your new data. For image segmentation, we are taking new data that looks like what our future data may look like, and you're training the models, and you're trying to come up with this model. But this one is a generalized model. It has been pre-trained, and it's a transformer. We just learned what a transformer is, self-attention, and scalability using parallel processing. That's what GPT stands for. And of course, it's designed for text generation tasks. You can think of text completion, machine translation, summarization, whatever, anything that has to do with text, then that's where GPT comes into picture. And this is exactly what I truly believe is going to automate a lot of jobs that has to do with text. For example, lawyers. Their core skill is about, there is a precedent set about certain situation. Back in 1989, someone had the same type of, case in Oklahoma, blah, 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 blah. All of that, it's fraction of a second for GPT. So I think those guys are going to be affected a little bit. In what way, we'll have to wait and see. But anything that has to do with text, then GPT has the ability to do an equal or definitely, I think a better job, but definitely equal job for sure. Okay, with that, do I have any more? Yeah, of course, you will hear the term one-shot learning quite a bit. And GPT is emphasizing on this decoder part where to achieve the dream of one-shot learning, right? So what does one-shot learning mean? Did I explain it anywhere here? Well, before reading what's on the screen here that you guys can easily read, one-shot learning basically means learning without any training, without providing any training. Okay, few-shot training is you provide a few trainings and then you get a few images. I mean, one shot is basically one. You know, you're providing your one thing as the training, and then it's giving you the answer. Few shot training is you're providing few instances and you're training the model. So GPT, just a quick historical information. Obviously, there are many people who I think developed similar language models using transformers, but the one developed by OpenAI is definitely a transformer-based model with a focus on decoding. We already talked about it, not the encoding part, but on the decoding part. And these models, especially GPT-3 and 4, now they demonstrated impressive capabilities in this zero-shot and few-shot learning, right? So we have seen that, where they can learn new tasks with no examples. Basically no examples. You're like, hey, can you explain something? You know, can you explain how supernova are formed? It's not like you trained it on, all this phenomenon. It just got trained on so much data, and it remembers and it gives you the right answer. And one limitation of GPT is that it has a tremendous amount of size in terms of number of parameters and the computational requirements of the model. I'll do a quick calculation in a second to show you what that actually means. So it is a bit challenging for if you as an individual or a small startup want to create practical applications out of it, to train from scratch a model like that. Just to have a quick look, what happened back, I should have put years here. This is pretty, starting from 2019, and this evolution took it's not decades we're talking about, it's few months in some cases. So I'm just showing you two things: original GPT model, GPT-1, and GPT-2, original one, medium, large, and XL. So the original GPT has 110 million parameters. I should say, it still has, obviously, if you want to use it, 110 million parameters, so you can train it easily on Colab. I mean, that's not much. It's easy, and it's pretty small. It's 12 layers, 768 hidden, and 12 heads. I don't think they mentioned what they trained these models are. Well, at least in this screenshot that I took from the Hugging Face. By the way, the GPT models can be downloaded from Hugging Face website, and this is they also have a repository of trained models in natural language processing, but also in other areas. So just check it out. This is a direct screenshot from their page. And GPT-2 has 768 hidden, but let's just focus on the parameters. This one's got 117 million parameters. The medium one, 345 million. The large GPT-2 has 774 million, and now you're getting into 1.5 billion with the XL right here. So how do they actually compare? Now I thought of how to put it on a visual to show you the difference between these models. And if you look at these models right there, if you think of GPT-1 as a small-sized pebble, GPT-2 also has a few, 1.5 billion. GPT-2 original has only 117, but let's just say, okay, it's 774 or 1.5 billion here. If GPT-1 is a small pebble on our beach, GPT-2 is like a small asteroid floating around. And GPT-3 is a small gas giant like Jupiter, and GPT-4 has 4 trillion parameters. That's almost like our sun. And GPT-5, I don't know how large it's going to be. Probably our galaxy, but I seriously doubt. Galaxy is much bigger compared to our sun. Maybe our solar system size, I would say. But this is the main reason for me to put this up here is for you to appreciate how between each evolution, it's actually growing in a pretty large way, right? So that's my attempt at showing you how the size differs between these. Now let's compare between GPT-2, 3, and 4. I'm taking the best of GPT-2 right here. So GPT-2 XL is 1.5 billion parameters. So if that's the case, now let's look at GPT-2. It was released in 2019, 2020 GPT-3, and 2022 was GPT-4. So let's focus. There's a lot to study here, but let's focus on a couple of things. One is the model size itself. You see 1.5 billion to, that's a pretty big difference, to 175, that's more than 10 times, to 4 trillion. So why does it matter? Why do large models actually matter? Well, they matter because they give us the increased capacity to learn and represent complex patterns. And they exhibit better performance in terms of accuracy, generalization, and language understanding. In other words, it's basically the larger the model, the better the response is in terms of remembering very long sequences and understanding the context. Talking about context, the number of tokens is also kind of important because the token capacity basically means the maximum number of tokens the model can handle during processing. That directly relates to the model's ability to handle these long sequence of text. If it only has ability, for example, 10 tokens, then the sentence can only have like 10 words, and that's pretty much it. And it doesn't know what happens before and after. 8,000 tokens at a time means you can have paragraphs of text going into the training, so it can understand the context much better. So token is, like I explained, a basic unit of text. It can be a word, but it can be part of a word, because I think this BPE or byte pair encoding actually does, I know it actually does, part of the word. And I have an example in the next screen in terms of, to give you an understanding of what this byte pair encoding is. The way it works is it iteratively merges the most frequent pairs of characters. For example, if you have, again, I have an example in the next screen, so why even think of it? So let's jump in. So if you have a sentence like this, Digital Srini is a good resource for Python coding tutorials, which is an absolute fact. I know you guys know that. And how does BPE Vocabulary, how can it break it down? It can break it down as this. Instead of digital and Srini and ease, a, good, it could break it down as D-I-G, I is already there, so T, and AL can be 1, SR, EEN, and so on all the way. So the tokenization, when you put all of those together, you can see the sentence right there. And it helps handle rare and out of vocabulary words by breaking them, as you can see, out of vocabulary. For example, Digital Srini is not in a vocabulary, right? I mean, is a good resource for Python coding tutorials. They're all in the vocabulary. But this is not. That's not something, that's not an English word, but it kind of helps handle these out of vocabulary words by breaking them into smaller units. Maybe it could have broken it down into digit, AL, and something else that kind of makes sense. In this specific example, so this word was split into D, I, G, I, and so on. And it's basically useful in improving the performance of language models. And GPT definitely uses this BPE type of tokenization. So I'm introducing you to certain terms that hopefully make it easy when you listen to other tutorials or when you read any articles about GPT. Finally, now, can we train our own model? That's the plan for the next tutorial using GPT-2, but why GPT-2? Why not train GPT-3 or GPT-4? Well, let's see what does it take to do that. Here is a paper that I highly recommend reading. It's literally hot out of press. This is, I'm doing like the second half of April. I'm recording this video in 2023. And this paper, I think, is also from April 2023. But it talks about open and efficient foundation for language models. And why am I referring you to this paper? Because here they give us an idea about what does it take to train these large models. They trained a 65 billion parameter model, and they processed around 380 tokens per second. And that's on a A100 GPU, 2048 of them. So A100 GPU is super expensive, as you know, from NVIDIA. And they subscribed to, or they purchased, I don't know what they did, but they have 2048 of these 80 GB RAMs, and they were processing 380 tokens per second on this one. And it took 21 days for 1.4 terabytes. I'm like, okay, so that's enough information. So let's do some math by taking this information. So quick estimate. I looked at Azure and I also looked at Google. It's about $3.50 to $4 per hour to subscribe to a 180 GB GPU. Okay, so let's do that. Let's subscribe to 2048 of them, of these GPUs at $3.50 per hour for 21 days. And if you do the math, it comes up to a little less than $4 million. I don't know about you, but I cannot train my own GPT model. I wish I could. I had that type of money to throw at a GPT model and train it, but that's only the training, the money for training. We haven't even included, that's just for the GPU rental. We haven't included the overhead that comes from the training data itself, because they train these models on the entire internet plus a lot more, like all Wikipedia and a whole bunch of other stuff. So that needs to be tokenized, that needs to be loaded into the RAM, and that takes up more overhead. So it's definitely much larger than $4 million, but luckily these guys have the funding that have the funding that they need to actually develop these models, but we don't. So we are going to train a smaller model, which is GPT-2, using a small data set, and understand. I want to give you a good feel for what is it? What is GPT-2? Like, can I use my own text? That's exactly what we're going to do in our next tutorial. Again, I am not going to write my own architecture for GPT-2. We are going to take the pre-trained model and actually take that and put that to test. We're going to take GP2, the small, medium, and large models, and then let's go ahead and train on our own document and start asking questions from that specific document. There's a lot to learn, believe me. That's why you need to hit the subscribe button. Let's go ahead and meet in the next tutorial and keep learning.